At the heart of modern Rome, where asphalt roads lie layered over the traces of thousands of years of history, there stands a structure that needs no signposts, no introduction, yet still forces every gaze to pause. That structure is the Colosseum. The Colosseum was not born to be beautiful. It was not built to serve art, nor to be admired for its elegance. Its original purpose was blunt and cold, to host massive public spectacles where humans and animals fought, where life itself became entertainment, and where the power of the Roman Empire was displayed before tens of thousands of eyes at once. Yet if we see the Colosseum only as a blood-soaked arena, we misunderstand its true nature. Behind those fractured stone walls lies not only violence, but science, engineering, organization, and systems thinking at a level rarely achieved in the ancient world. The Colosseum was built at a time when humanity had no internal combustion engines, no mechanical machinery, no structural steel, and no reinforced concrete in the modern sense. And yet it has stood for nearly 2,000 years, enduring earthquakes, wars, looting, and the relentless erosion of time. This endurance is not a matter of luck. It is the result of a civilization that understood how to apply scientific principles long before science had a name. To understand the Colosseum, it is not enough to stand before it as a tourist. We must turn back time to the 1st century AD, to a moment when the Roman Empire had just emerged from civil war, chaos, and the collapse of an old dynasty. The new regime needed a symbol powerful enough to calm the population, grand enough to declare that order had been restored. The Colosseum was born in that context, not merely as an architectural project, but as a declaration of power carved in stone. Turning that declaration into reality required solving a series of engineering problems that would remain formidable even by modern standards. An enormous elliptical structure, nearly 50 meters tall, more than 500 meters in circumference, capable of holding over 50,000 people, and built in a remarkably short time by ancient standards. Every one of these figures represented a scientific challenge. The first challenge was materials. Most of the stone used to build the Colosseum was travertine, a hard and durable limestone quarried primarily in Tivoli, about 30 kilometers from Rome. In the modern world, such a distance is trivial. In the 1st century AD, transporting tens of thousands of stone blocks, each weighing between 10 and 40 tons over that distance, was a monumental logistical problem. The Romans did not approach this challenge impulsively. They understood that transportation was an integral part of construction, not a secondary task. For that reason, travertine blocks were not transported in a completely raw state. At the quarry, they were roughly shaped in advance, excess material removed, and flat surfaces prepared for securing ropes and stabilizing the load during transport. This preliminary processing reduced weight, lowered the risk of cracking, and conserved pulling force throughout the journey. On land, the blocks were placed on wooden sledges or large wooden carts. Rather than dragging them directly across the ground, the Romans used wooden rollers placed beneath the load. As the sledge advanced, the rear rollers were moved forward, creating a continuous cycle. This was a simple mechanical principle, yet extremely effective, allowing massive weights to be moved without metal wheels or modern bearings. However, the most important transport method was not over land, but over water. The Tiber River, flowing through Rome, became an ancient highway. Stone blocks from Tivoli were brought to the river, loaded onto flat-bottomed wooden barges, and floated downstream or hauled upstream by human labor. Water transport dramatically reduced pulling force, allowing heavier loads to be moved with far less risk. The Romans clearly understood what modern transport science confirms: water is the most efficient medium for moving heavy objects. None of this would have been possible without a vast and tightly organized labor force. The Colosseum was not built by a handful of craftsmen. It was the product of a state apparatus involving tens of thousands of slaves, skilled builders, and military engineers. Each stone block had a defined route, a designated team, and a pre-calculated schedule. This was a centralized logistical system, resembling an early form of industrial production. But delivering stone to the construction site solved only half the problem. The more critical question was how to ensure that the structure would not collapse. The Colosseum was built on land that had once been an artificial lake belonging to Emperor Nero's palace. This meant unstable, waterlogged ground. The Roman solution was to excavate foundations 12 to 14 meters deep, then pour a special concrete mixture composed of lime, volcanic ash, and rubble. This mixture not only hardened effectively, but continued to bond over time, forming a massive foundation slab that distributed the weight of the entire structure evenly. Rather than concentrating loads on a few critical points, the Colosseum's foundation spread forces across its entire perimeter. This made the building more stable against ground movement and external stresses. It is a foundational principle of modern foundation engineering applied nearly 2,000 years ago. Above the foundations rose the arch system, the core element of the Colosseum's structural strength. Instead of relying on fixed solid walls like those of pyramids, the Romans employed hundreds of stacked and interconnected arches. An arch does not push weight straight down. It redirects forces sideways, then channels them through columns into the foundations. This allowed the structure to bear immense loads, conserve material, and create vast interior spaces. The arches did not function independently. Together, they formed a force-distributing network. If one section weakened due to damage or stress, adjacent sections could absorb the load. This is why the Colosseum did not collapse in a chain reaction, even after numerous major earthquakes. The building was divided into 4 main levels, each using different materials. The lowest level employed the heaviest stone and bore the greatest load. Higher levels used progressively lighter materials. This distribution mirrors the structure of living organisms: a strong base, a lighter upper body. Loads from the seating tiers were transmitted through the arches, down the columns, and into the foundations, with no single point carrying the entire burden. The circular corridors inside the Colosseum served more than circulation. They were integral to the load-bearing structure and also functioned as shock-absorbing voids. These empty spaces reduced overall mass, lowered pressure on the foundations, and limited the spread of cracks. This approach closely resembles modern seismic design principles. The Colosseum, therefore, was not merely an ancient stadium, it was a fully integrated engineering system where every element served multiple purposes. Science, engineering, and architecture were inseparable. And it was precisely this integration that allowed the Colosseum to outlast its own era. If we view the Colosseum solely as an engineering achievement, we understand half its story. The other half lies in how the structure was designed to serve power. The Colosseum was not just a place for spectators, it was where the Roman state confronted its population directly. More than 50,000 people gathered in a single space, focused on a central stage, reacting collectively to carefully orchestrated events. This was a rare social phenomenon in the ancient world, and to control it, the Romans used architecture as a tool of governance. The internal organization of space reflected Roman social hierarchy. Seating was not assigned randomly or for convenience. It followed rigid social ranking. The lowest seats, closest to the arena, were reserved for the emperor, senators, and elites. Higher levels corresponded to lower status. Women, slaves, and the poor were pushed to the highest tiers, farthest from the center, with inferior views and experiences. Notably, this social order required no coercion. No guards stood beside each spectator. Architecture itself enforced hierarchy. physical position became a direct reflection of social status. This was an early demonstration of how designed space can regulate behavior without explicit commands. The Colosseum's circulation system also reveals scientific thinking about crowd control. Ring corridors and stairways guided movement naturally, minimized crossflows, and reduced chaos. The entrances and exits allowed tens of thousands to enter and leave in a short time, an achievement many modern stadiums still strive to match. The Romans did not merely build a strong structure, they built a system for human use. They understood that crowds follow patterns. Properly guided, they move in order. Poorly guided, they become dangerous. The Colosseum's architecture was the mechanism of that guidance. The structure also controlled emotion. The immense elliptical space, with the arena at its center, produced a powerful psychological effect. Every gaze converged, every reaction was amplified. The roar of tens of thousands became not just sound, but a shared emotional experience. Within this environment, the emperor was not a distant ruler. He was visibly present, seated at the symbolic center of power. The Colosseum became a political stage where authority was performed before the people. The games were not merely entertainment, they reinforced the bond between state and populace, bread and spectacle, exchanged for loyalty. From a social science perspective, the Colosseum was a massive experiment in human